Okay, let's take a look at molecular formulas to molecular shapes. So what we're going to be doing now is we're going to be combining information that you've learned from the last section and this section to predict molecular shapes starting with the molecular formula. So we're going to begin by drawing the Lewis structure. So if we're trying to figure out the shape of tellurium tetrachloride, tellurium goes in the center surrounded by 4 chlorine. You connect them with single bonds, you count up the total number of valence electrons, you'll realize you have an extra pair. That extra pair goes on the central atom tellurium because it is in the 5th period. It can accommodate more. It can have an expanded octet. Then what we're going to do is we're going to classify it with a designation of central atom A, 4 X's for my bonded groups, and then 1 lone pair of electrons E on my central atom. So this is AX4E. AX4E is a seesaw shape. Okay, we're going to do the exact same thing on the next page in the practice problems. So let's take a look here. So if we're looking at this Lewis structure, we have our central atom A. I have 5 bonded groups at X's. So this is AX5. I have no lone pairs of electrons on the central atom, and I just realized I am looking in the wrong book. Okay. And so that means this will be trigonal bipyramidal. We're not going to draw the diagram here. In order for us to draw that diagram, we would have to go to how to properly draw 3-dimensional diagrams with hash marks and triangles, and I'm just not going to do that. For B, this is A for our central atom, XE, and I have 4 bonded groups, which are my X's. I have 2 lone pairs of electrons on my central atom. So this designation is AX4E2. That means this is square planar. So remember, that's where we had a lone pair of electrons above and below the central atom, and then you had 4 bonded groups in a plane and then looked like a square. Okay? Now, if we go on to number 2, here we are completing a table where we're drawing the Lewis structures, predicting the shapes of the molecules. CCl4 would look like this. And this is AX4 for our designation, and that means the shape would be tetrahedral. For B, PF3, P is your central atom with 3 fluorine coming off of it. This is AX3E, and this is trigonal pyramidal for its shape. SCl2, sulfur in the middle with chlorines attached on either side. This would be your Lewis structure, which is AX2E2, and this is bent or angular. Let's turn to the next page. Okay. Now, let's talk about going from polar bonds to polar molecules. Recall you talked about electronegativity in biology. Electronegativity increases up and to the right on the periodic table. Fluorine is the most electronegative element, with francium as the least electronegative element. All of the numbers in the boxes are electronegativity values here. They're also on the back of your book, conveniently, okay? So what we're going to be doing is, they're in the upper right-hand corner of each box on the back of your book, just so you know. what we're going to be doing is we stated at the beginning of this section that an essential part of understanding and predicting chemical and physical properties is determining the shapes of their molecules, and then the most significant consequences of molecular shape is related to polarity. So what does that mean? So if you have a polar molecule, it affects physical properties like the melting point, the boiling point, the solubility, and it can also influence how reactive something is. So remember that if you have a bond that is polar, that means that it has unequal sharing of electrons, which is caused by a difference in electronegativity. So if I'm taking a look here at HCl, hydrogen, you'll notice, has an electronegativity of 2.1, chlorine is 3.0. You find a positive difference between the two. And here we get 0.9, and when you fall within a certain range, then you have a polar molecule. And here, the chlorine being more electronegative, I'm going to abbreviate that with En, than hydrogen. That means that you're going to have the electrons drawn to chlorine in the bond, and that means you will get a partial negative charge on the chlorine atom and a partial positive charge on the hydrogen atom, representing that there is a charge separation within the bond. So this would be a polar bond, okay? And you would represent that with these symbols, the lowercase deltas, and then also you can use this arrow pointing in the direction of the more electronegative element with a cross on the more positive element on the other side, okay? Okay, so HCl is a polar molecule. And if a molecule has more than 2 atoms, the shape of the molecule as well as the polarity will play a role in determining if the entire molecule is itself polar. And we're going to be taking a look at polar molecules, and then we will talk about whether those polar molecules, well, what kind of intermolecular forces those polar molecules will have. So let's start by talking about carbon dioxide. So carbon dioxide has a structure that looks like this. Yes, I have 2 carbon double bond O bonds. I just need to look at one of those bonds to figure out if one of those bonds is polar. So if you look at carbon, which has an electronegativity of 2.5, and oxygen is 3.5, I subtract that difference to get I want a positive difference, and then my change in difference in electronegativity is 1. And this is a polar bond, and that means that you're going to have a partial negative on the oxygen and a partial positive on the carbon, okay? You could also have arrows pointing in the direction of the more electronegative element, oxygen, on the periodic table. Now, this is a linear, because it's MX2, this is a linear molecule. And what that means is you have identical bond dipoles pointing in the opposite direction of each other, because this is 180 degrees. And that means that for this shape, the bond dipoles will cancel each other out, and that's how I get a nonpolar molecule. So the first thing that you have to do to figure out if you have a polar molecule is determine if you have a polar bond. If you have a polar bond present, and then you would look at the shape, is it a symmetrical shape where those bond dipoles can cancel? And if they can, then you would have a nonpolar molecule. And if they don't, then you would not have a nonpolar molecule. Let's take a look at water for a second, just to sort of convey to you what a polar molecule would also look like if the bond dipoles didn't cancel out. So for a water molecule, oxygen has an electronegativity of 3.5. Hydrogen is 2.1. So 3.5 minus 2.1 is an electronegativity difference of 1.4. So this is a polar bond, which means you could have the arrow pointing in the direction of oxygen. You could also have a partial negative on the oxygen with partial positives on the hydrogen. Now, although I have polar bonds, I need to look at the shape. This is a bent molecule because it is AX2E2, okay? Now, this means that these bond dipoles point in the general same direction, which is upwards, so they're reinforcing each other. So that means that this is a polar molecule, okay? Let's go on to the next page. What about if I have two molecules with the same shape that have polar bonds? So let's take a look at these two AX4 molecules. The first one is known as carbon tetrachloride. So chlorine is more electronegative than carbon, which is why it has the arrows pointing in the direction of the chlorine. And AX4 is tetrahedral. On the right-hand side, I have CH3Cl. Carbon in the carbon-hydrogen bond is more electronegative than hydrogen, so therefore you have arrows pointing in the direction of carbon. And then in the carbon-chlorine bond, chlorine is more electronegative than carbon, so the arrow is pointing in the direction of chlorine. So in this case, yes, this is AX4, which is also tetrahedral, but you will notice that the bond dipoles are pointing in the same general direction here in this molecule, but in this one they are not. Now, tetrahedral and linear and trigonal planar and a couple of others are symmetrical molecules. So when you have the four bond dipoles pointing in opposite directions in a symmetrical molecule, those bond dipoles just cancel out and it's nonpolar. So that's why this is a nonpolar molecule. Okay, so I can take this liquid and I can dissolve other nonpolar substance in it. But if I'm looking over here at this substance, you will notice that the bond dipoles point in the same general direction, therefore they are not going to cancel out, and this would be a polar molecule. Okay, so if the bond dipoles cancel, I'm going to underline this for you down here. If the bond dipoles cancel, then the molecule is nonpolar. If the bond dipoles don't cancel, then the molecule is polar. So let's turn to the next page. And let's take a look at some of the guidelines for determining if a molecule is nonpolar or polar. So the first one says, when the peripheral atoms in a molecule are identical and arranged symmetrically around the central atom, any bond dipoles that exist will cancel and the molecule is nonpolar. Well, how do you know if it's symmetrical? Well, if it is linear, trigonal planar, tetrahedral, octahedral, trigonal bipyramidal, or square planar, then it is symmetrical. If the molecule is asymmetric, either due to its shape or composition, any bond dipoles that exist will not cancel typically, and the molecule is polar. Now, in most cases, symmetrical molecules are AXM molecules with no lone pairs on the central atom. All of these molecules have identical peripheral atoms. They will be nonpolar regardless of the bond dipoles that exist. Now, I personally find it easier to use a flowchart to predict. So what I'm going to do is I'm going to mute this for a second, And I'm just going to give you a flow chart that you might find really useful. So when you're trying to figure out if a molecule is polar, the first question that you want to ask is a polar bond present? That means if you have one type of bond, then just find the electronegativity difference and figure out if it falls within the polar bond region. Can you even see that? No, that is too high. So let's take it down. So you can't see above here. Okay. So there's the first question you ask. Is a polar bond present? So like I said, if you have one type of bond, calculate the electronegativity difference, and if it's polar, great. If you have more than one type of bond in a molecule, then you need to calculate the difference in electronegativity between each type of bond until you figure out if one of them is polar. So the question, once you ask this question, if the answer is no, there is no polar bond present at all, then it is a nonpolar molecule. If the answer is yes, then you have to ask yourself, is the shape symmetrical? Okay, what do I mean by that? That means, is it linear, trigonal planar, tetrahedral, octahedral, trigonal bipyramidal, or square planar? If the answer is no, it's a polar molecule, because the bond dipoles aren't going to cancel out. If the answer is yes, then you need to ask yourself, are the atoms bonded to the central atom identical? That means, are the peripheral atoms in the molecule identical? If the answer is no, then this is a polar molecule. That's because your bond dipoles can't cancel. If the answer is yes, then this is a nonpolar molecule. And that's because the bond dipoles can cancel, okay? Okay, so an example of a nonpolar molecule would be like H2. That is a nonpolar bond between the hydrogen atoms, so that's why it's a nonpolar molecule. If you're looking at something like NH3, for example, the nitrogen-hydrogen bond is polar. Is the shape symmetrical? No, it's trigonal pyramidal, which is not one of the symmetrical shapes listed. So that's why it's a polar molecule. If you're looking at CH3Cl, a carbon-hydrogen bond is polar and a carbon-chlorine bond is polar. Is the shape symmetrical? Yes, because this is tetrahedral. Are the atoms bonded to the central atom identical? No. I have 3 hydrogen and 1 chlorine on the central atom carbon, so the bond dipoles don't cancel. That's why it's polar. But if you have CH4, the carbon-hydrogen bond is polar. It is tetrahedral, which is symmetrical. Are the atoms bonded to the central atom identical? Yes, they're all hydrogen. That's why it's nonpolar, because all of those bond dipoles cancel out. So you can use this flow chart when you're doing the problems So for instance, if we are looking at the sample problem here, and I'm going to try and make it so that you can kind of see the sample problem while we are keeping the flow chart up. Here's the Lewis structure for chlorine trifluoride. We need to figure out the shape and if it's polar. This is AX3E2, okay? Now the difference in electronegativity between chlorine and fluorine is 1.0 because fluorine is 4.0 and chlorine is 3.0. So the positive difference between them is 1.0. So that means that we have a polar bond. So I have a polar bond present. Is the shape symmetrical? Well, when it's AX3E2, it is T-shaped. T-shaped is not listed as one of my symmetrical geometries. So the answer is no. So that is automatically a polar molecule. So if you turn to the next page and you take a look at the practice problems, these practice problems here are summarizing the symmetric and asymmetric molecules in terms of their notations and their shapes. Okay, so for this, I'm just going to fill this in for you. So AX3, AX4, AX5, AX6, AX2E3, AX4E2. The shape of these molecules would be trigonal planar, tetrahedral, trigonal bipyramidal, octahedral, linear, and square planar. For the asymmetric molecules, the notations AX2, E2, which is bent or angular, and then AX3E, which is trigonal pyramidal, and then AX4E, which is seesaw, AX3E2, which is T-shaped, and AX5E, which is square pyramidal. Okay. Now, in number 2, they've asked us to complete the table. They gave us the Lewis structures, and they want the notations and the shapes and whether it's a polar molecule or not. So if you take a look at A, this is AX3. That means this is trigonal planar. Polar or not? Well, the XO bond is polar. If I look at the electronegativity values, that's a difference of 1.0. And then the carbon-hydrogen bond is also polar. So I have a polar bond. Trigonal planar is a symmetrical geometry, but I don't have the same atoms bonded to the central atom, so the bond dipoles don't cancel, so therefore that is a polar molecule. So you have the bond dipoles pointing in this direction, okay? B, this is AX3E. And this is trigonal pyramidal. And our nitrogen-hydrogen bond is a polar bond, and nitrogen is more electronegative, so you've got the bond dipoles pointing in that direction. And so a polar bond is present. Trigonal pyramidal is not one of my symmetrical geometries. This is a polar molecule. Let's take a look at C. This is AX5. So this is trigonal bipyramidal. And if I look at phosphorus and chlorine, chlorine is 3.0, phosphorus is 2.1. So that means that chlorine is more electronegative, and this is a polar bond. And is this a symmetrical geometry? Yes, trigonal bipyramidal is. I have the same atoms bonded with the central atom, so the dipoles cancel, so this is not a polar molecule. Let's move on to intermolecular forces. Okay, now, the chemical bonds that are within molecules are known as intramolecular forces. So what that means is if I'm looking at this molecule here, then the bonds are between the individual atoms. So those are your intramolecular forces. Attractive forces between molecules and between ions and molecules are known as intermolecular forces. So what that means is if you're looking at the interactions between these two molecules, these are intermolecular forces.
No.
Now, intermolecular forces aren't as strong as chemical bonds. Let's start by talking about dipole-dipole forces. These are attractive forces between polar molecules only. Polar molecules have a positive and a negative end, known as a molecular dipole. And the positive pole of one molecule is going to be next to and attracting the negative pole of an adjacent molecule. And this is known as your dipole-dipole force. This results in higher melting and boiling points because it's going to take more energy to pull apart those molecules and get them into a different state of matter. So the more polar a molecule is, the stronger its dipole-dipole force. Here you can see you have HCl and HCl. These are both polar molecules. You have a partial negative charge on the chlorine and a partial positive charge on the hydrogen. And the partial negative on the chlorine causes it to be attracted to the partial positive on the hydrogen. So this interaction here between the molecules is known as your dipole-dipole force. Now, let's talk about hydrogen bonds. Hydrogen bonds are a special type of dipole-dipole force. And they are stronger, a stronger example, I should say, of the ordinary dipole-dipole force. And that's because here you're going to have polar molecules that contain a hydrogen atom bonded to either nitrogen, oxygen, or fluorine. So you already learned about these in biology. So you will either have an HN, HO, or HF bond in each molecule. And they're going to be very polar because hydrogen has a low electronegativity. So you're going to have a huge difference in electronegativity between these two atoms, which means there's going to be a lot of electron density removed from hydrogen within the bond, which is going to leave this hydrogen with a partial positive charge on it, and you have this partial negative charge on the NO or the F. So what happens is the partially positive hydrogen in one molecule is going to be attracted to a lone pair of electrons of the partially negative atom of the other molecule. And that attractive force is so strong, and that's going to allow for the tiny electronegative. Let me get to the next page here. That's going to allow that tiny electropositive hydrogen, since it's such a small atom, it's going to allow it to get so close to the lone pair of electrons on the partially negative nitrogen, oxygen, or fluorine of the other molecule that it creates this intense attraction known as a hydrogen bond. So what that means is that if you look, I'll come back to this in 1 second. If you look here, you will notice that you have your partially positive hydrogens in water attracted to oxygen in water, has 2 lone pairs of electrons, but one of those lone pairs of electrons is going to be attracted to the hydrogen in a neighboring water molecule. And it is this here that is your hydrogen bond, the interaction between them, okay? Now, hydrogen bonds cause really high boiling points. So you'll notice here that they've given you some compounds, and these compounds, this would be hydrogen with oxygen, hydrogen with sulfur, selenium, tellurium. So these are hydrogen bonded to an element in group 6A or 16. But you'll notice that when you have water, which has an OH bond in it, that has the ability to hydrogen bond with another water molecule, so that's why it has such a high boiling point. Same thing down here for hydrogen bonded to fluorine. So this has the ability to hydrogen bond with another HF, which is why its boiling point is so much higher than expected, because you'll see HCl, HBr, HI. Those are in the same group, which is group 17 or group 7A. HF is so much higher. NH3 also has the ability to hydrogen bond, and you notice that it has a much higher boiling point as well. The DNA double helix, you'll also see that it has the ability to form hydrogen bonds. And let's go on, that's through the base pairs of DNA. And then let's talk about London dispersion forces, and then we'll finish up with ion dipole forces. So for London dispersion forces, they are often abbreviated LDF. And when we have non-polar molecules, will only have London dispersion forces. However, all molecules have London dispersion forces because these are the weakest forces, and these are caused by electrons that are just moving constantly, and they may end up in one location over another, which causes this polarizability of a molecule. So let me explain for a second. If I'm looking at a chlorine, that might be better if I show you this image here. If I'm looking at a chlorine molecule, which is a chlorine bonded to another chlorine atom, okay? So you may have equal distribution of the electrons within each atom, but what happens if at one moment in time the electrons just move? And let's say they are more this way than they are over here to the right-hand side. So if the electrons are just shifting to one side very temporarily and instantaneously, you'll get a partial negative charge wherever those electrons have a higher density, and a partial positive charge on the other end. Okay, so what happens is, if we're looking at two different atoms and you have a partial negative on one side and a partial positive on the other, that will influence the electrons in the neighboring atom to shift as well. And then you'll get an attraction between them. However, this is slightly incorrect because this is just a whole molecule. You're going to get interactions between the molecules. So you'll have your partial negative on one